Okay, so let's see if we can remember what we're doing here. We have a linear transformation, T linear transformation, and it goes from between two spaces, right? So T is a linear transformation going from V to W, right? Two vector spaces. And what else do we have? What else do we have? We have, is that it? What are we trying to do? Can you remember? Matrix representation. Let's remind us of the topic. Matrix representations of linear transformations between vector spaces. Right? So we want a matrix that you know captures the behavior of T, and so right these things are not Euclidean space. Right? We want some matrix. V is n-dimensional, say, n-dimensional, and R is m-dimensional, and we want some matrix A so that the linear transformation going from n to m, Rn to Rm, basically does somehow parallels in some sense the behavior of T from V to W, right? And right, so somebody gives us one basis, right? Somebody gives us a basis V1 to Vn of V, and somebody gives us another basis W1 to Wm of W, right? Those things give us, with those bases, we get the coordinate maps, right? We get these coordinate maps, which we call P and Q. Right? And we wanted, right? We want T sub A to make this diagram commute. In other words, so that for any V in V, TV hit with Q is the same thing as PV hit with T sub A. Which, using the coordinate map notation, is the same thing as saying that the coordinate vector with respect to the F basis of TV is the same thing as A times the coordinate vector of V with respect to the E basis. And remember, it turned out that call A was obtained by doing what? Do you remember? You take the basis vectors from E, you run them through T, bring them down to here, and then you use those guys as the columns of your A matrix, right? A was obtained by taking T Vi with respect to F basis as the ith column. The ith column of A. Right? And that's basically where we stopped last time. So just to wake you guys up, let's do an exercise. So let S be the span of e to the x e to the x, and x squared e to the x. Okay, and let D be a linear transformation from this vector space S to itself, where D is differentiation with respect to x. Okay, and I'd like you to find the matrix representation of D with respect to that basis, e to the x e to the x squared e to the x. Okay, that should take you maybe 3 minutes, 2 or 3 minutes. Okay, turn to somebody else and say what you're doing, even if you haven't finished. Yeah, it's up to Itsung behind you. She never has anyone to talk in the previous class and in this class. She doesn't have anyone to talk.
Yeah, so you run the and then you have to write what you get in terms of because it's the same basis. And then you only transpose it by those.
Yeah, I was just going to. Yeah.
Okay. So what do you do? How do you do it? How do you get the matrix representation? Or somebody want to tell me what it is? Mia?
Is it 1, 0, 0?
Which way are you going? Down.
1, 1, 0. 0, 2, 1.
Yes, that's it. Anybody? Well, I'm not going to ask if anyone didn't get it, but so how do you get this, Mia?
You do the transformation with respect to the first basis, and then express it with respect to the second basis, like the coordinate vector.
Which actually is the same basis.
The same basis.
So you take each one, right? Take each one, run it through the first times the second plus through the first times the second, right? And you get first times the second plus the first times the second. Right? So you take each of these guys, right? And you express it with respect to the second basis, right? So we've got S, right? R3, we're using the same basis in both cases, right? So you take the first element, run it through, find its coordinate vector. Right? The coordinate vector of e to the x with respect to this basis is just 1, 0, 0. Right? Coordinate vector of this thing with respect to the basis is 1, 1, 0. And the coordinate vector of this thing with respect to the basis is 0, 2, 1. Okay. And then those things are the matrix. Okay. And we can see that this thing behaves as it should. Okay, so I hope things are sort of falling into place. One comment about the book's presentation. The book states it like this. So, book's presentation. Okay. So the same setting and all, right? And they say for any v and v, we know v equals x1 v1 plus xn vn. The claim is that there exists a matrix in an n by n matrix that represents T in the sense that ax equals y if and only if tv equals y1 w1 plus ym wn. So this is the book's expression of the matrix that represents the linear transformation T. Okay, but it's the same thing. It's the same thing, right? This is saying that ax equals y when this y is the what's y? Y is TV expressed with respect to the W basis, right? And what's x? X is the expression of the coordinate vector of v with respect to the E basis, right? So what they're saying is that A times the coordinate vector of v with respect to the E basis equals the coordinate vector of TV with respect to the F basis, right? Which is the same thing. So just to translate from their presentation to the presentation that I've given. Okay, they're saying exactly the same thing. I don't like phrasing it this way. It seems clearer to me to state it this way in terms of diagrams that compute. Okay. Kathleen, any question? Any questions? Okay, so matrix representations of linear transformations between vector spaces. We'll do something strange right now, which is we'll do this where the vector spaces are already themselves Euclidean spaces. Okay, so this will be so here's one simple case of the so you have T going from Rn to Rn. Okay, that's a linear transformation. And you'll see why we're doing this in a minute. Like what's the point of doing it in this simple case? So again, we're going to have a basis, V1 through Vn, basis Rn, and F, W1 through Wn, basis in Rm. Okay, and then so this is they state this as a theorem. Okay. So suppose you are doing what we just did in the case where the vector spaces are Euclidean spaces. Okay, so instead of having an abstract V and an abstract W here, we have Rn and Rm. So it's still the same. It's still the same problem, right? You've got Rn to Rm like this. You have your bases. You have your bases, which give you maps to Rn and to Rm, right? These give you maps, what we call P and Q, down to Rn and Rm, and the theorem is going to say something about the matrix A that makes this commute. Okay? The theorem says the matrix representation of T with respect to E and F is A1 through AN, where AI is W1 through WM inverted times TVI. Well, I equals 1. Okay, so this might look, convoluted or something, but this is just exactly, we're basically saying exactly the same thing that we said over there. Okay, right? Somebody gives you a transformation between vector spaces and says, what's the matrix representation? You already know how to do it, right? What's the matrix representation? Just do what we did before. Just apply the previous work. Right? Apply the previous calculation, right? We know that A sub I is going to be what you get when you map VI, right? You map VI through T, and then express it with respect to the F basis, right? We know that, right? That's exactly what we wrote over here. You did it just now yourselves, right? And then, what is TVI with respect to the F basis, right? What's TVI with respect to the F basis? Well, we did this before. It's going to be W1 dWm to the minus 1 times TVI. Right? You take the basis elements. You take the elements in the basis, and you put them in a matrix, and you invert it, and then use that thing to get the coordinate vector. Right? Just to remind you, and myself actually, right? Because, right? W1 through Wm times TVI with respect to F is TVI. Right? So TVI with respect to F is going to be you invert this thing and multiply on both sides by it. Right? Right. Is this clear? Right. Remember, you have this vector, and you like the coordinates with respect to the f basis. What are the coordinates with respect to the f basis? Well, they're the coordinates that you use to reconstruct this thing from the wi's, right? And when you multiply this thing by that, you're going to get a linear combination of the wi's, right? With these coefficients, with these entries as the coefficients, right? So this is what happens, and so that tells us that TVIF is going to be the w guys inverted times TVI. That's what we wrote here. So that's that. So this really isn't a theorem. You should say it's just like a corollary of the previous work. But it's handy in the sense that what you see then is that thus A could be expressed like this: W1 Wm inverse TV1 TV2 and TVm. So it gives you a nice way of calculating. Yeah.
You just got that part from when we were doing change of bases a few weeks ago. Right?
That's right. Yeah, that's when the change of basis 3.5. So, which one could calculate by reduction? Right. If somebody asked you to figure out what this was, what you could do, is to put all the w's on one side, and then the TVI's on the other side, right? And then row reduce down to the identity on the left, and then on the right hand you would have A, right? Because once you reduce this left thing down to the identity, that means that you've multiplied the left side by the inverse of this, and so the right hand side would be A. Let me do it. Let me do an example. Should I do an example of that? Is that people want to see that? Okay, do an example. Okay, so here's an example. This is problem 18A from the text. So you have one basis. You have a linear transformation from R3 to R2. Here it is. It takes x1, x2, x3. And maps it to x3, x1. Okay. You have a basis of the first space, U1, U2, U3, where U1 is 1, 0, -1. U2 is 1, 2, 1, and U3 is -1, 1, 1. Okay. And you have a basis of the second space, B1, B2, where B1 is 1, -1, and B2 is 2, -1. Okay. And somebody would like the expression. somebody would like the matrix representation of T with respect to these two bases. So what's the matrix representation T with respect to these two bases? Right. So from T down 3 down 2. Down here, down here. 3. Okay. And so we can just, at this point, we can just do the calculation. We say, okay, we know what's going to happen. A is going to be B1, B2 inverse, TU1, TU2, TU3. That is to say, 1, -1, 2, -1 inverse times TU1 is -1, 1, TU2 is 1, 1, TU3 is 1, -1. And if you work it out, it turns out to be -1, -3, 1, 0, 2, 0. And let me just check that that actually does do what it ought to do. So for example, if we look at 1, 0, -1, right? And we run that thing through the T matrix, right? What does that go to? That goes to -1, 1, right? If we take that thing and express it, so this is U1. If we express U1 with respect to the E basis, right? With respect to the E basis, well, that's just going to be 1, 0, 0, of course. Right? That'll be 1, 0, 0. And if we hit that thing with the A matrix, what happens? Well, we get -1, -3, 1, 0, 2, 0 times 1, 0, 0. Right? And that'll give us -1, 0. -1, 0, and you see that this is TU1. If we take TU1 and express it with respect to the F basis, with respect to the B guys, what do we get? We get -B1, right? So this is -1, 0, right? And those things end up to be the same. So this matrix, at least on this element of the basis, and in fact on all elements of the basis, it works. Right? It represents the linear transformation. Okay. I don't know if you're bored or if you're confused. I can't tell. Are you bored or confused?
I'm more the second one.
Okay, close your eyes for a second. Raise a finger if you're confused. Okay, open your eyes again. Okay, thank you. Okay, so a couple of people confused, not too many. So just remember what we're doing, right? We're trying to find, somebody has given us a linear transformation from R3 to R3, R3 to R2. Right? We have these two bases. Right, we have these two bases. I'll talk to you, Henry, since you openly admitted that you're confused.
Yeah, I'm fine with
Great,
with that.
great. Okay. So you've got these two bases, E and F. Right. right? Those give you the maps. Those give you these coordinate maps down to here. Right? And we're looking, as before, we're looking for a matrix that completes this. Right? We're looking for a matrix that completes this. Turns out that the matrix is going to be, right? You get it by, just as by before. You map each guy. You map each. You map each element of the basis over, and then take the coordinate vector with respect to the second basis, and you put those guys in columns, and that's it. Yeah, Henry.
Well, one question. So when you get U1 with respect to E, how
Yeah.
did you get to the 1, 0, 0?
Okay. So over here, so we got the matrix here.
Yeah.
Anyone confused about how we got the matrix? Anyone confused about how we got the matrix? Be honest. Confusion? No? Okay, so everybody knows how we got the matrix. Over here, all I'm doing is checking. Like, I'm just checking. In fact, I'm checking only on one element. Okay, just for the heck of it. Did it actually work? So let's look at U1. When we run U1 through T, we get -1, 1, right? Because what does T do? It says, I'm going to take x3, x1, right? So it says, I'm going to take x3, x1, right? Okay. And then I express that thing with respect to the f basis. Well, what's -1, 1 with respect to the f basis? Well, it's negative of the first guy, right? Right. This thing, this -1, 1 is -1 times b1 plus 0 b2, right? So its expression is -1, 0, right? Its coordinate vector, the coordinate vector of this thing with respect to the f basis is -1, 0.
Okay, yeah.
Okay. Now I run this thing the other way. I say, let's take this u1. Let's look at its coordinate vector with respect to the e basis. Well, u1 with respect to the e basis is 1 u1 plus 0 u2 plus 0 u3. So its coordinate vector is 1, 0, 0. Right? Its coordinate vector is 1, 0, 0. Right? So I take that thing and I hit it with the A matrix, and not by miracle, I get exactly the same thing. Okay. And so this matrix actually does behave. If we checked it on the other basis elements, we'd see that in fact it agrees.
Thank you.
Okay. So the moral is actually if we change the bases, we get a different matrix. Even though this is a matrix going from R3 to R2, right? This is a matrix going from R3 to R2, right? What's the representation of this with respect to the standard basis? With respect to the standard basis, well, right, this should be, it will give us R3 first, right? So it will be 0, 0, 1, and then it will give us, oops, right? This is the matrix representation of T with respect to the standard basis, right? You see what it does, right? It gives us, in fact, x3, x1, right? This is the representation of T as a matrix directly, right? Okay. But if we represent it with respect to a different basis, we get a different representation. Okay. If we represent it to a different basis, we get a different representation. Okay, so this is actually the point you want to get out of this. That changing the basis, you can get different representations of the same linear transformation. Okay, and that leads us into the next section, 4.3, which is called similarity. So we finally escaped 4.2 after I don't know how many lectures. 5 lectures? 4 lectures? It was long. Okay. So in this section, we're going to be dealing with linear operators. Okay, and so the author makes this distinction between linear transformations and linear operators, saying that linear operators go from the same vector space to the same vector space. To me, this is still a linear transformation. I think most people would still call this a linear transformation. But anyway, so we'll be dealing with linear operators, and we'll be dealing. Yeah, I think the author. This is going to be linear operators is a specific kind of linear transformation. Linear transformation is the general class, and linear operators are those, only those which go from the same vector space back to itself. So we'll be dealing with these linear operators and their matrix representations with respect to a basis B, okay? A single basis for the vector space. Okay. So the picture is like this, right? You've got V to V, right? Your basis gives you a map to Rn, right? On either side, you're using the same basis to get a coordinate map, right? And you've got this matrix, which I'm going to denote by A sub B, because it depends on the basis. So let A sub B denote the matrix representation with respect to B and B. So we're using B, the basis B on both sides. It would make more sense, maybe. It's probably more illustrative to say A sub B, B. Anyway. Okay. So notice if we change B to B prime, some other basis, we change the matrix. Our question now is, what is the relation between the two matrices? Right, if we change the basis, well, we change this matrix. Right? Is there some relation between these things? It turns out that they are actually very closely related. Before we show that relation, let's recall something. So given a vector space V and bases E and F, where one was V1 to Vn, and the other was W1 through Wn, we found the transition matrix takes the coordinate vector with respect to E to the coordinate vector with respect to F. Right? Do you remember how we did it? One, you express V1 as S11 W1 plus S21 W2 plus SN1 Wn. Express all the V's in terms of the W's. And then you took the matrix of those coefficients. Right? Right, this is how we did it. You express one basis in terms of the other, and then you take those coefficients. And remember that it was the transpose of these. It's not it's not directly these coefficients, but the transpose of these coefficients. Okay. Yeah. Mia.
What's the transpose?
It was so right. So look,
So
I've got
it's-
W1 S11. Look at the first row here is the first column of
Okay, yeah, that's
this
what I
here.
thought.
Yeah.
I didn't know.
Yeah. So the transpose. You don't take it directly here, but you take the matrix here and then you transpose it,
Oh, okay.
and that gives you the transition matrix. Okay. So I hope everybody remembers this game that we played a few sections ago. Okay. Just one comment. What is S? What is S? At this point, we can say something a little bit more about S. Right? S is the transition matrix that takes the expression, the coordinate vector with respect to E to the coordinate vector with respect to F. We can think of it in a slightly different way now. So you have V, right? V, we've got the E basis, and that gives us a map down to Rn, right? This is we take the vector and map it down to its coordinate vector with respect to E, right? And we also have V, we also have this other basis, F. That gives us a map from V to the coordinate vector with respect to F. Right, so what's S? S is actually, if I call this P and I call this Q, S is actually P inverse followed by Q. Right, because that goes from the coordinate vector with respect to E to the coordinate vector with respect to F. Right? That's the map. You invert these coordinate vector maps are isomorphisms. So if you invert this guy and compose it with that guy, then you get the map you're looking for. Okay, so here is the theorem that if T is a linear operator, and you have two bases, E and F are bases of V, and S is the transition matrix from E to F. Right. In other words, S takes the S goes from one coordinate vector to the other coordinate vector. Then, in fact, A sub E is S inverse A sub F S.
What is A sub E?
Yeah, right up here. right back here. So remember, A sub B denotes a matrix representation with respect to that basis.
E and then A sub F.
Yeah. So remember what we're trying to do. So we have this linear operator. We have two bases. We have matrix representations of the operator with respect to E and one with respect to F. And the question was, what's the relation between those two matrices? Right? Right. We had this, right? We had this, some basis. Somebody gives you some basis, and that gives you a representation. But you change the basis to some other basis, you get a different representation. And the question was, what's the relation between those two matrix representations? The answer is that one is what's called a conjugate of the other. That is, one guy, to get from one guy to the other, you take this thing and you conjugate it by the transition matrix. Okay. This matrix goes from E to F. This matrix goes from E to F. Right? So if you conjugate the matrix representation to F by the transition matrix from E to F, that gives you the matrix representation with respect to E. Okay. And so they are very closely related to each other. They are conjugates, what's called conjugates of each other. Okay, so that's not really a good time to stop, but we'll stop here, and then we'll say it again at the beginning, and then explain it.